related to itself. Suppose A is a friend of itself, ये भी हो सकता है, A is a friend of itself, A is a friend of B, B is a friend of A. अब ये जो लाइन होता है इसका मतलब जो एजेस होता है ये भी बहुत बहुत तरीके के होते हैं. एक जो ऐसा है कि A इज अ फ्रेंड ऑफ B एंड B इज अ फ्रेंड ऑफ A, मतलब इसमें कोई डायरेक्शन नहीं है. और एक होता है कि डायरेक्टेड ग्राफ एजेस, जिसको हम एरो से डिनोट करते हैं. तो सपोज ये यहाँ पर है से A और यहाँ पर है से B. सो हियर वी कैन से दैट सपोज इसको हम नया रिलेशन बोल सकते हैं कि बोरो मनी. So if we consider this kind of relationship, then using a directed graph, we can say that A has borrowed money from B. तो अगर हम इसको ऐसे डिनोट करें इस एरो से, तो इसका मतलब ये नहीं होता कि B has borrowed money from A, ये नहीं होता. तो A जो डायरेक्टेड ग्राफ होता है तो ऑर्डर्ड पेयर्स में होता है. तो A, B रिलेशनशिप बिटवीन A टू B को हम ऐसे बोलते हैं A टू B इज नॉट इक्वल्स टू B टू A. लेकिन अनऑर्डर्ड ग्राफ्स में हम बोल सकते हैं A, B, A टू B इज इक्वल और इक्विवेलेंट टू B टू A. हाँ, तो ऐसे सिंपली यहाँ पर भी हो सकता है डायरेक्टेड एजेस फ्रॉम इटसेल्फ. तो ऐसे बोरोड मनी फ्रॉम इटसेल्फ तो नहीं हो सकता, लेकिन कोई और रिलेशन हो सकता है जो ऐसे डायरेक्टेड हो. तो इसमें यहाँ पर मैंने थोड़ा गलती कर दिया था एरो देके, तो एरो नहीं होता अनडायरेक्टेड ग्राफ में. तो A is related to itself, A and B are related to each other in case of a undirected graph. In case of a directed graph, A is related to B, मतलब A to B ये होता है. मतलब अगर तुम सिंपल A 2D ग्राफ्स में सोचो, तो से A is a room and B is another room. So in case of a directed graph, we can say that there is a path from A to B such that we can move from A to B but not B to A. This is very important to understand the difference between the directed graph and undirected graph. Any problem, if you can see that in the later lectures or in any problems you can solve in lead code, you can understand that this the if we can just change one word in the question from directed to undirected or from undirected to directed, the entire solution gets changed, right? So let's see a typical graph. Let's draw a typical graph. So let's say there is 1, 2, 3. So as you can see so this is a graph, say G. So this when you denote a graph, you denote it using two sets E and V. This is the how to represent a graph. So this is the representation where E is the set of edges and V is the set of vertices. right? uh, अब इस ग्राफ और ग्राफ्स में और भी काइंड्स होते हैं तो सपोज here we can see that we can move from A to B, that is there is a edge between A 1 to 2 which is unweighted. There are two kinds, weighted and unweighted. Here unweighted means that all the edges, say this edge 1 to 3, 1 to 2 and 2 to 4, they have the same cost. Means if you move from 1 to 2 and 2 to 4, the time it takes in or the unit cost it takes is the same. But another way is that there are weighted edges. Weighted edges. So suppose say one. So suppose there is a graph G where 1, 2, 3, and 4 here represents 4 towns. Okay. So let's say 1 to 2, say 5 kilometer, 2 to 4, say 10 kilometer, and say 1 to 3, say 2 kilometer. So here you can see that the vertices are the towns itself. So 1, 2, 3, and 4. So and the edges are the roads which connect two towns. So here you can see that there is a direct road from 1 to 2. There is a direct road from 1 to 3, but there is no direct road from 1 to 4, which means that you cannot directly go from town 1 to town 4. And here we have assigned some weights because this is a weighted graph. So in case of a weighted graph, that there is some value that is being added to the edges. So here there can be different types of weights. Here I have given the weights as the distance between the two towns or the distance of the road. Uh, so here between 1 and 2, the distance is 5 kilometer. Between 2 and 4, the distance is 10 kilometer. Between 1 and 3, that is distance of 2 kilometers. So uh, uh, just seeing this, what comes in your mind is that the road maps, the Google Maps. So exactly this type of things, these graphs are used by Google Maps for to calculate the shortest distance. So if you say you want to go from Howrah station to IIST Shipur, and you enter it into Google Maps. So Google Maps uses the graphs as uh, the the junctions or the say the crossings, the road crossings as the vertices or the nodes, and the roads connecting between them as the edges. And similarly, as I have given here the distance, they also give either distance or based upon real-time traffic, they give time, say 10 minutes. And not today, in the next session, you will learn how to actually calculate the minimum distance between uh, two sets of points in a graph, like exactly like or in a similar way like Google Maps or any distance finding algorithm does using BFS. We will do it in the next session, but today we're just doing the basics. So this is kind of a graph, and there can be like this also, say A, say B, say C, let's see. So let's do a directed graph, say the one-way roads. The direct analogy that you can have here is there are two junctions or two crossings A and C, and there is a one-way road. कोलकाता में बहुत ट्रैफिक हो जाता है तो रोड्स को वन वे कर देते हैं, तो सिमिलर टू लाइक दिस देयर इज से a one-way road. So let's say you are in point A, and there are three more points, say C, B, and D. So if you can see that if you follow this path, say let's write it here, say A to C, and so you move from A, your starting position is A, then you move to C, and then say you move to B, and then again using this road B to A, you move to A. So here you can see that in this directed graph, if you start from A, you are again moving back to A using some sets of roads. So this is another kind of structure within the graph. This is what we call a cycle. So the what is a cycle? A cycle is a structure within a graph. It is said to exist if if and only if we start from some point, and after following some roads or some edges, we can again come back to that node. So this is the cycle: A to C, C to B, B to A. There are a lot of algorithms like cycle detection, and based on cycles, there is a bipartite coloring, bipartite matching, etc., etc. So trees and graphs is a very vast thing. There are lots and lots of algorithms. So this is a brief definition of some of the major kinds of graphs, I would say, that you would encounter in the CP. And what now? Let's come to say trees. So let's draw a graph. So as you can see, this is a graph. There are four verti- um, vertices A, B, C, and D. There are also four edges: one, two, three, and four. So what you can say that tree is a special kind of a graph. So when can you say a graph as a tree? You can say a graph as a tree when all the nodes are connected. All the nodes are connected. So in this case, let's take another. No, okay. So what does connected mean? So this is another terminology: connected and unconnected graphs. So the term connected means that if you start from any vertex, uh, is anyone trying to tell something? Yeah. So connected means that if you start from any vertex, say A, B, C, or D, any vertex, you should be able to move to all other vertices using some of the edges. So if we start, and this should be true for all vertices, that means um, if you start from say A, you can move to C, uh, you can move to D, you can move to B. If you start from B, say there is an edge between B and A, so you can move. So if you start from B, you can there's a direct edge between A to B, so you can move to A. There's a direct edge between B and D, so you can move to D. There is no direct edge between B to C. So does that mean that it is not connected? The answer is no. It is connected. Uh, how is it connected? So there is no direct edge, but that is not the condition. The condition is that you should be able to move to all the other vertices using some of the edges. It doesn't mean to. It doesn't state that you can only move once. So if you can move from B to A, and then there is an edge between A to C. So I move from B to A and A to C. So I have reached C from B. So all the edges, all the vertices are reachable from B. So this is a connected graph. Now, if say there is another edge E, and so now is B. So is E reachable from B? Say I move to D, there is no way to go to E. I go to A, there is no way to go to E. I move to C via A, there is no way to move to E. So now the graph has become disconnected. That means that there is some node from which it is not possible to reach some other node. Okay, so these are the two ways, two terms, connected and disconnected. And there is another condition for a graph to be a tree is that there would be no multiple edges or cycles or self loops. So these are, so we have come to another some terms, multiple edges. We have come to another terms, multiple edges, self loop, cycle. So cycle, I have told you what is a cycle. So here A to B, B to C, sorry, B to D and D to A. So we can again come back to A after following a path, say A, B, B, A, B, D and A. So this is a cycle. So this is definitely not a tree. So already the condition is false, but for the other terms, what is multiple edges? So multiple edges is that here I said that there is a relationship. So what are edges? Edges are relationships or between two nodes. So it is possible that there can be multiple relationships between two nodes. Just like the example of a path. Say there is a town A, there is a town B, and there is a road of say 5 kilometers. It is possible that there is another town, another road which moves to some village or something, and it takes 10 kilometers. So there are now two roads between A and B. So there are multiple ways to reach from A to B directly. That is there. So here we can see that there are two relations. So this is what multiple edges means, that there are multiple, edge between two nodes. And self loops, as the name suggests, is related to itself. Means suppose there is a road starting from town A, traverses to some sightseeing, and then again comes back to this road. Say has a a distance of say 10 kilometers. So this is a self loop. So if the nodes are connected, if there are no multiple edges, no cycles, and no self loops, then we can say that it is a tree. So now I would like to ask you a question. So if say there are uh, 10 nodes in a tree, mind it, tree, what is the number of vertices? Sorry, the edges. Can someone tell me?
9.
Exactly. So there, this is like this. You should be able to memorize this. In case of a tree, the if the number of vertices is say v, the number of edges is equals to say e equals to v minus 1. This you should memorize.
Actually, you can prove this that if the number of edges is greater than v minus 1, so let's say you have a number of edges is v, so there will be always a cycle or a multiple edge, because between n persons there can be n minus 1 relationships, right? So if there are more than n minus 1 relationships, so there will be something like more than one relationship between two people, or there is a cycle of relationship. So A goes to B, B goes to
Exactly.
C,
Exactly.
and C again goes to A. So like this, you can visualize that if there are more than v minus 1 edges, there will be either a cycle or a multiple edges or self loops. Means A has a edge to A, like that. And if there are less than v minus 1 edges, so in that case either it will be not connected, means the whole tree is not connected. Means if it has less than v minus 1 edges, the whole means all the v edges nodes will not be connected, because to connect every node we at least require v minus 1 edges.
Yes. So if you see, suppose this is the tree. How can we say that this is a tree? Uh, so there are four edges, all are connected. You can see if you can just go through it and show that this is connected. Just a minute. So this is connected. There are no self loops. There are no multiple edges. So this is a tree. You can say that this is a tree. So as per our definition, that there has to be v minus 1 edges, which is 4 minus 1 is 3. So there are 3 edges. So how can you put another edge over here? Any way, if you want to add a edge here, it will be a multiple edge. Or if you want to add a edge over here, it will be a cycle. 1, 4, and 2 becomes a cycle. If you want to add a edge over here, this becomes a self loop. So there is no way that there can be edges more than that or less than that. So uh, if there is less than that, so we have to delete some node. So let's say that this node is deleted. So there is no way to move from 2 to 1. So this graph becomes disconnected. So uh, this condition. So this is a fact that there has to be v minus 1 edges. There are some basic ways or the basic definitions. If why if you see that to draw a tree like this, why is it called a tree? A lot of you know people ask why is it called a tree? Why the name tree? So if you draw it like this, so does it look like a tree? It does not. But if you actually turn it upside down, uh, so now it looks a similar kind of a tree. So this one, this is called a root, from where it start. We can start the traversal. In after a few minutes, Anish will teach you about the traversals. So you can say that wherever we can start, we can call that a root. You can also make two as the root, right? So if you redraw the tree like this, two, here one, here three, and here four, and here five. Uh, this can also be made root. So any node you can start, so that becomes a root. And
uh,
all the yeah
yeah, means if the tree is undirected, means the edges are not directed, then only you can make any node as a root. Okay, so but
yes
if the edges are directed, so there will be a particular, means a specific root. Any node you can't take as a root if the edges are directed. If the edges are undirected, as in this case, then you can consider any tree as the root. Okay.
yeah. So I was So now, uh, say the last. So another way is to define is at the levels. If you consider one as the root, it is at the topmost way. So we also consider is at level 0, and the next set of nodes is at level 1. This set is at level 2. There is another question that also comes is level order traversal. Uh, Very common question for interviews, level order traversal. Then you can exploit this fact: level order traversal, vertical traversal, diagonal traversal, this things, the levels. And the leaves are from where you cannot go anywhere, the last set of nodes. So if you start from 1, you come to say 3. Let's just for simplicity take a directed one. So from 3, you cannot go back to go to somewhere, even if it was an undirected graph. From 1 to 3, you can come to 3, and then there is only one path from 3 to 1, but you have already uh, been, checked 1. You have already been to town 1, say. So there is no way to go from town 3. So this becomes a leaf. There is, so there 4 is also a leaf, 5 is also a leaf. There are also other definitions like complete graph, and what are the others? I forgot. Complete graph.
There
I
is
think it's
also degree. Degree ta bolo.
degree. So degree, that's important. So for any graphs of trees, so the degree of a node is the number of nodes, other nodes to which it is directly connected. So let's say, so let's say take the example of 2. So 2 is not. Let's first take the example of a undirected graph. So if it was an undirected graph, 2 is directly connected to 1, 2 is directly connected to 4, 2 is directly connected to 5. We can move from 2 to 3 via 1, but it is not directly connected. So the degree of 2 is equals to 3. And in case, these are some corner cases. In case of a self loop, it adds 2, the outgoing and the incoming also adds. So it will become plus 2 equals become 5. In case of an directed graph, so there are two types of degrees. There is an in degree, and there is an out degree. One is DEG plus and one is DEG minus. Which one is one? I forgot. It is not important, but it is for understanding. Out in degree is the number of edges from which is coming towards the edge, towards the node. So in this example, 2, if we consider 2, this edge 1 to 2, it comes towards 2. So it is an in edge. Here is only 1, so it is 1. Out degree is similarly the number of edges which is coming out of the node. There are 2. We can go from 2 to 4. We can go from 2 to 5. It is so 2. And any other terminology, Anish? Am I forgetting something?
Nothing as such, but
Any other terminology or something?
acha, level is also known as depth. Okay,
Yeah. So level or
same thing.
equals
Level or
to
depth.
so you may be asked this. You may get a question say, find the number of nodes at depth 1 if you consider root as 1. So the answer will be node 2 and node 3, so it will be 2. And let's say how we can store the graphs. As I said earlier, that there is some special ways to store the graphs. Uh, if you don't do in those ways, then you will not be able to solve the problems. That too. So if we want to say store the edges, uh, there are two ways: adjacency list and adjacency matrix. So what is an adjacency list? Let's take an example. Three, four, five. So adjacency list for an undirected graph is the number of nodes from which we can. Acha, one thing that I forgot to mention is another term called neighbor. So neighbor is the nodes which we can reach from a particular node in one move. For example, we can reach from node 1, we can reach to node 3 and node 2 in one move. So the neighbors of 1 is 2 and 3. So using that definition, the adjacency list is the way of storing the list such that for each node, we are storing the its immediate neighbors. So we can store it using vector in C++ or a list in Python. So what will be the adjacency list here? So if the node is 1, its adjacency list will be 2 and 3. Uh, for 2. So now anyone tell me what will be the adjacency list for 2 using this graph? Is there anyone or sub there? Yeah, tell.
1, 4, and 5.
Yeah. So 1, 4, and 5. So one thing that some may confuse, that we have started from 1, we have come to 2. So there is no need to go to 1. So this may not be in the adjacent list, but no, that is wrong. Adjacent list में सब neighbors होते हैं. If you come from that or you want to go to that, doesn't matter. Similarly, C3 का होगा only 1, 4 का 2, 5 का. So this is the efficient way to do the to store the graphs. Uh, there is, so I will also tell you when it is efficient to do the adjacency list and adjacency matrix. So similarly, in case of an adjacency matrix, by the name suggests, there would be a matrix where on each side there will be the nodes 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. So in case of an adjacency matrix, just a second. So in case of an adjacency matrix, we put either ones or zeros in the matrix. So we put a 1 in case if there is a direct edge between that two nodes. So here between 1 and 2, there is um, an edge, so we put 1. 1 to 3 we have 1. From 1 there is nothing, so 1 to 1 0, there is no self loop. 1 to 4 no, 1 to 5 no. uh, from 2 to 1, 2 to 2, 2 to 3, 2 to 4, 2 to 5, 3 to 1, 3 to 2, 3 to 3, 3 to 4, 3 to 5, 4 to 1, 4 to 2, 3, 5, 0. So this would be the adjacency matrix. So there is a interesting fact for an adjacency matrix of an undirected graph. If you carefully see that this is a symmetric matrix. I hope you understand the symmetric matrix. Means it is a mirror image if we put a line across the main diagonal. So 1 to 2, 2 to 1. So this is quite understandable, because there is 1 to 2 be here or 2 to 1 be here. There is no directed one. So if this becomes similarly, if this becomes a directed one, so 1 to 2, then 1, this is your, say this one is the starting, this one is the ending. So 1 to 2 would be 1, but 2 to 1 will be 0. And so now, looking by this, you can quite easily understand that two are somewhat different of different ways of storing it. So now each one has its own benefits. Now if the graph and now say um, find the uh, say there is, at some point of the question you have to find that there if there exists an edge between, say 1 and 3. So if this is an adjacency list, uh, let's say this is stored in a vector 2D vector or a hash map. So you come to 1 and you check all the elements using linear searching. So this will somewhat roughly take and O of length time. So in the worst case, all edges would be connected. So it can take O of E time. But here you can directly tell is that if there is an edge between 1 and 3. So you go from 1 to 3, there is an edge, and you can say print yes. So this is 1. So going by this logic, a lot of you might directly say that adjacency matrix is a better way, time efficient way of storing the graph. But the answer is yes as well as no. Because say if the graph is sparse, suppose there are say 100 vertices, 1 to 100, and there are say only two edges, 1 to 2, and say 48 to say 55. So there are only two edges. Why would I need n square? So you can obviously see that there has to be n, or if we consider it by v vertices, v square space. Why do we need that? If we use an adjacency list, it would be only two spaces. Or if it is an undirected graph, it will be two. It will be 1 to 2, similarly 2 to 1, and also 48 to 55, 58. So it will be only four spaces. So if it is a sparse matrix, we prefer an adjacency list. If it is a dense matrix, then this linear searching, as I said earlier, the searching becomes difficult. So adjacency matrix would be easier. But practically, if you see the coding questions, the 90% times you would prefer an adjacency list, because there is rarely a very dense matrices given. Adjacency list. Is there any question up till now? Adjacency list, adjacency matrix. Is there any question? I don't think so. Anish, is there anything else?
No, no, no.
Okay. So talking to this. So now we will move to traversals of the graph. So Anish will teach you about the traversals. So सिर्फ स्टोर करने से तो कुछ नहीं होता. We have to move through the graphs, and based on that we can have some questions. So over to you, Anish.
So what do we do in DFS is that we start from the root, take one of its children, then take another of its children, and then go back to its parent, and then go to its another children. So basically what we do, we go on going deep until we find a leaf. Okay, so let's say we are starting from one. So our stack will be something like this. So first we have an empty stack, then we insert, so then we insert one, then we have its two children, 2 and 3. Okay, so we take 2, and then we go to one of the children of 2, so it's 4. So now 4 doesn't have any children, so what we do, we pop out 4 from the stack. So this is a LIFO system because 4 was inserted at the last, and it has been popped out, means at the first. Okay, so this is a LIFO system. So we first push 1, then 2, then 4. So you can observe that we are going depth wise, means 1, then 2, and then 4. Okay, so we are going deep. Okay, so after this, what we do, we pop out 4, and we print 4. So let's say our DFS traversal is something like this. So we print 4 here. Sorry, not print. We pop out 4, and now we have 1 comma 2 in the stack. Okay, so now 4 is visited. So we update visited 4 equals to true. Means this is an array we just keep to make sure that 4 means the nodes which are visited or not. So 4 is visited here, so we make visited 4 equals to true. Initially the visited array is false for every node. Okay, so now we make 4 equals to true, and now we check the last element of the stack, so which is 2 now. So we see that whether any children or child of 2 is unvisited or not. So 2 has 2 children, 4 and 5. So out of 4 and 5, 4 is visited and 5 is not visited. So we have one unvisited child of 2, 5. So we insert 5 in the stack now. So now we again take the last element of the stack and check that whether we have any unvisited children of it. So 5 doesn't have any children, so we pop out 5 and make visited 5 equals to true. And now the stack contains 1 comma 2. So now again the last element is 2. So 2 doesn't have any unvisited children because 4 and 5 are already visited. So now we pop out 2 also. Okay, so visited 2 is true now again. So now we go to, means now the stack is 1. So 1 has, so now 1 has 3 I has unvisited. So we, so now we insert 1 comma, means we insert 3 in the stack. So now the last element of the stack is 3. So 3 has 6 as its unvisited children. So we insert 6 here. So now we again check the last element of the stack, 6. 6 doesn't have any unvisited children of it. So we pop out 6. And now the stack is 1 comma 3. So now 3 has one unvisited children, that is 7. So we insert 7 in the stack, and again we check that 7 has any unvisited children or not. So no. So we pop out 7. So now the stack is 3. So 3 also now don't has any unvisited children here. Okay. So we pop out 3 also. So now it has 1. So 1 also doesn't have any unvisited children. So now the stack is empty. And we stop the iteration or recursion. So this is a pretty means general way of DFS traversal, and also while popping out, we also make them true. So I didn't update the visited array. So after 2, so visited 3 will no not 3 6 will be true. Similarly 7, then 3, then 1 will also be true. Means visited 7, visited 3, and visited 1 will be true. So like this we go on. So till here, anyone has any question? Then we can move on to the coding part.
What are we exactly searching here?
We are not searching here. We are just traversing the tree. Means we are visiting every node, basically of the tree.
So why is this process being termed as a search process?
Basically, it means, let's say if you have to search that whether 4 is present or not in that tree. So in that case, you can search in this way that if visit means if you get 4 anywhere in the stack, so you can return true. Otherwise, you can return false. So like that. So
Okay,
means
okay.
this is the application. Means you can use DFS to search something. Okay, so this is just the implementation. So because means if you have to search something, you have to visit all the nodes, right?
Yeah.
So here we are visiting all the nodes, and in DFS we visit the nodes in this way. Means we go on going deep till we don't have any children, or we don't have any unvisited children. We go on deep like this, and then after we have no unvisited children, we go back to its parent. Means we go back to the upper level or upper depth. So any questions? So it will be something like this. Something like this. And this is the whole operation from empty to another empty. So is there any question here? Then we can move on to the coding part. Okay, so we can move on to the coding part. So we can, the most easiest way to do DFS is to have a recursion function. So let's say we have a function called DFS. In the parameters, we have adjacency list, that is graph, and we have a vertex V. So the vertex V is the current vertex we are visiting. Okay. So yeah. So also we have an array visited, just as I told, to make sure that whether the vertex V is visited or not. So when we are visiting the vertex V, we will make visited V equals to true, because we are visiting V. So visited V will be true here. So after this, we will iterate through all the okay. So after visiting, we will iterate through all the nodes which are neighbors of V. So we can run a for loop for I in graph V. So basically, graph V contains the neighbors or the not children or the parents and children of V. Okay, so we will again check here that whether the uh, vertex I is visited or not. So if visited I equal false, then we will visit this node. So we will call the function DFS with the adjacency list and the current vertex with I and the visited array. Okay, so basically this is the full function. It is as easy as this. Means basically you don't have to write anything else to visit all the nodes. Like this, I can show you how this is working. Okay, so let's say we have this graph we talked before. Yeah, and in the main function, just and from the main function you just have to call this function with the adjacency list, and V will be the root, that is 1, and visited. Okay, so now the adjacency list will be something like this. Yeah, so the adjacency list of 1 will be 2 comma 3. Adjacency list of 2 is 1 comma 4 comma 5. List of 3 is 1 6 and 7. Adjacency list of 4 is 2. Adjacency list of 5 is 2. Adjacency list of 6 is 2. Adjacency list of 7 is 2. Okay.
Adjacency list of 6 and 7 are 3.
Sorry. It's 3. Okay. So now we are calling this function DFS graph. So graph is the adjacency list. Okay. So we are calling the function with the current vertex 1, and visited is false for every vertex now. Okay. So first we are calling 1. So visited 1 will be true, and now just okay. So now visited 1 is true, and now we are so now we are iterating through the adjacency list of 1. So list of 1 is 2 and 3. So visited 2 and 3 are false. So we are going to DFS 2. Okay. So now after going to DFS 2, we are making visited 2 equals to true, and we are iterating through the adjacency list of 2. So 2 has 1 comma 4 comma 5 in the adjacency list. Now since 1 has been already visited and visited 1 is true, we don't iterate, means we don't call DFS 1. Okay, because 1 is visited already, means 1 we have already visited. So from 2 we will call 4 and 5 only. So we call DFS 4 now. So now we make a visited 4 equals to true, and after we make the visited 4 equals to true, we check the adjacency list of 4. So 4 has 2 in it, but 2 is already visited. Okay, so from DFS 4, we don't call any DFS function. Okay, so after calling 4, we go back to DFS 2, right? Is this understandable? Means after DFS 4, we are tracing back to DFS 2. Is there any confusion here?
What did we do after DFS2, or rather
Okay,
after visited one actually?
okay, okay. Let me clear this. Okay, so let's say we have a stack here. So we are calling DFS 1 here. Okay, so in DFS 1, we are making visited 1 equals to true. And what was the adjacency list of 1? It was 2 and 3. So both 2 and 3 are unvisited. So we call from DFS 1, we call DFS 2. Okay.
How are we exactly accessing the adjacent lists of all the variables?
There was something like this, no? Graph V. So you can, instead of graph, you can consider ADJ. So that's how you are iterating through the adjacency list.
Okay. I
So
get
you
it.
are doing something like this. If visited I is false, so you call DFSI. Okay.
Okay.
So now since visited 2 is false, we are calling visited DFS2. Okay. So you are making visited 2 here true. Mind you, these are all in a stack. So in the stack, you first have DFS1, then you have DFS2. Because in recursion, you use a stack. So now you go to adjacency list of 2. So 2 has 1, 4, and 5. And let me draw the tree. Uh, Many might not get a reference. Okay. Yeah. So now DFS 2. So now since visited 1 is true, we don't call DFS 1 again. So after 1 we have 4. So we call DFS 4 now. So we make visited 4 equals to true, and we now go to the adjacency list of 4. So 4 has 2 in its adjacency list. So now 2 is visited again. So is there any unvisited element in the adjacency list of 4? We don't have any unvisited element in the adjacency list of 4. So we don't call anything from DFS 4. So we take out this from the stack. So the last step was DFS 2. So we have visited 1, we have visited 4, now we have 5. So we call
How
DFS.
did we take out the DFS 41?
So what was, I mean, just, so what was the function, right? Like this was the function, right?
Yeah. Something like that. Yeah.
So we are making visited p equals to true. Okay. So ignore this DFS 5. This was for just understanding. After this line is executed, DFSI. After this, we are coming back to the control is something like this. No, let's say we have a statement here. Print V. So after this function is called and everything is done in DFSI, we will be coming back to this line, right? Yes or no?
Was there any function called print in the previous page?
Okay, okay. If there is not a function, let's say, so adjacency list has many elements, right? So let's say, for example, first I was equals to 4. So after DFS 4 is called and everything is being executed in DFS 4, we will be again going back to this line, right? Because it is a for loop and
Yes.
every element. So now after 4 we have 5. So after DFS 4, everything in DFS 4 is being executed. We go back, the control goes back to this line, and
Yes.
we go from 4 to 5, means I becomes from 4 to 5. So now we will call DFS 5. So what is happening in the stack? So we have DFS 2 already in the stack, DFS 1 and 2. Okay. So after DFS 2, we have called DFS 4. So after everything is done in DFS 4, we are going back to this line. So everything is done in DFS 4. So we are removing DFS 4 and now we are calling DFS 5 because I is 5 now after being 4. So
Okay,
now,
okay, okay. I
we
get it.
have the DFS 5 in the stack. So again, DFS 5 has adjacency list 2. 2 is already visited, so we don't have anything to do, means we don't call anything from DFS 5, and the work of DFS 5 is done. So we remove DFS 5 from the stack. So now we have DFS 2. So every node is visited of 2 also, means 4, 5 and 1 is already visited. So we don't have any other things, means extra other things to call from vertex 2. So DFS 2 is also popped out from the stack and we go to DFS 1. So after 2 is done, so we go to the next one, that is 3. So we call DFS 3 now. So adjacency list of 3 is 6, 7 and 1. 1, 6 and 7. So 1 is already visited, so we don't call 1. 6 is not visited, so we call DFS 6. So 6 doesn't have any unvisited children, so we don't call anything from DFS 6 and we take out DFS 6 from here. And next one is 7, so we call DFS 7 here. So 7 also doesn't have anything to do right now. Uh, so we take out DFS 7 now. So now we have 3. So the adjacency list of 3 has 1, 6 and 7. So 1, 6 and 7 are all visited. So we take out DFS 3 here. And now we have 1. So uh, the adjacency list of 1 has 2 and 3. Both of them are visited. So we take out now 1 also. So the stack is empty now, and see that we have visited every node of the tree. So is there any confusion or question?
I think I still didn't get that part of switching from one leaf to another, like from 4 to 5 and from 6 to 7.
Okay, so let's say you have this condition in the stack. So now DFS 4 will be called because 4 is not visited.
Yeah,
Yeah. So adjacency list of 4 has what?
only 2.
2 is visited.
Yes.
So is there anything extra we call from
No.
DFS? So after let's say we are calling DFS 4 here. So DFS 4 has nothing extra to do now.
Okay, yeah.
Okay, so after everything, the function has ended of DFS4. DFS4 has done its work. So when we are calling DFS4 here, so after DFS4 has done all its work, so this line has executed its task.
Yeah, okay.
So after this line, the control goes back to this line because in a for loop we are iterating. After this line is executed, where does the control goes back?
Again to the for loop.
For loop. So what is adjacency V here? 1, 4, and 5. Till this, is it
Uh,
clear?
no, I really didn't get it. How is 1, 4, and 5 coming?
What is V here? V is 2, no? So let's say V is 2, okay, and adjacency V is this. So the first element, let's don't consider 1, okay. For the time being, we have 4, 5, and 1. So 4 we have now. So visited 4 is false, right?
Okay, yeah.
Okay. So now we are calling DFS 4.
Okay.
After, let's say, DFS 4 has done all its work, okay.
Yeah.
What will be the control going back? Control will be back to this.
Yeah.
So what is the next element of what will be the next value of I?
Okay, it will be 5. Okay.
Okay, so visited 5 is false.
Yeah, false.
So now it will call DFS 5.
Okay, okay.
So now you have got it.
Okay, okay. It's I've got it. Yeah. Right. Thank you.
So is there any other question? Means this was the basic implementation of DFS using stack. I mean, sorry, using recursion. Next day we can discuss about DFS using stack and BFS. So if you don't have any question, we think we can stop here. So is there any questions in graph, means the terminologies and DFS? Otherwise, we can stop. Also, like if you want to practice DFS, so you can go to lead code and under the problems section, you have this one, depth first search, and you can solve this. You can start with the easy ones. You can start with the easy ones. You will get a hold of it. And if you want to do means some harder problems, you can go to code forces and you can use the tag. Let's say you go to the problem set and you can search here that DFS and similar. Okay, so this tag will give you problems which are solved using DFS. So you can solve the starting from the easiest ones like this. You can start solving from this. Also, if you want to get a basic hold of it, I would suggest you should start from lead code. You should do the easy ones if you want to get a hold of it.